In the case of this heavy bomber, the first barrier was legal rather than physical. In 1987, investigator Tony Mazzolini visually located a largely intact Boeing B-29 Superfortress on a remote target range at Naval Air Weapons Station, China Lake. The aircraft carried serial number 44-69972, had been delivered to the United States military in March 1945, and later served with a radar calibration squadron that named its aircraft after characters from a well-known animated film, giving this bomber the nose art and designation Doc. The recovery stakes were procedural before they became mechanical. Because abandoned military aircraft on live or dormant testing ranges remain federal property, the team first had to secure a lawful transfer of title. The Navy controlled the artifacts at China Lake, where Doc had been transferred in 1956 to serve as a ground target for ordnance and weapons effects testing. Over the following decades, other aircraft on the same range were destroyed by test activity, while the Superfortress remained largely intact on the Mojave Desert hardpan. To release the title for the B-29, the Navy conditioned the transfer on an artifact exchange rather than an ordinary scrap sale. The civilian recovery team had to procure, restore, and deliver a B-25 Mitchell finished in a Marine Corps configuration acceptable to the National Museum of Naval Aviation. That one-to-one trade reflected the Navy's heritage priorities. Releasing an Army Air Force's B-29 would produce a display-ready naval aviation artifact in return. The entire burden of sourcing, funding, and executing the required restoration fell on the civilian group before they could begin their own primary recovery operation. Satisfying this mandate took 11 years of negotiation and physical work on the surrogate aircraft. During this prolonged delay, the recovery team still did not control the China Lake bomber. They could not take possession of the airframe or begin the actual extraction until the exchange was finalized and the title formally transferred. The team was negotiating against the procedural risk that the B-29 could be damaged by continued range activity, whether further in the open, or be treated as range debris before the B-25 trade was finalized. Once the federal government released the title, the legal constraint gave way to the aircraft's physical condition. The desert had produced a sharply divided preservation state. When the civilian recovery team finally gained physical access to the site, they did not find an intact aircraft ready to roll. They found an aluminum shell that had been subjected to decades of continuous environmental weathering. That divided condition turned the first engineering task into triage. The arid environment had preserved enough primary structure to make extraction possible while destroying enough secondary material to make any towing attempt unsafe without inspection. Before applying force, the team had to identify which components could still carry load and which had failed. The defining characteristic of the China Lake Basin is minimal moisture. Without continuous exposure to saltwater or high humidity, the galvanic corrosion that normally consumes abandoned military aircraft was severely throttled. The thick, stressed skin aluminum components that form the wings, fuselage, and empennage retained their structural integrity. The main load paths remained largely intact. This structural baseline was the critical factor that made a physical extraction theoretically possible, as the airframe would need to bear significant handling loads during a recovery operation. While the low humidity protected much of the heavy metal structure, the extreme solar radiation and thermal cycling aggressively attacked everything else. The high desert sun effectively baked the airframe. Constant exposure to ultraviolet light, heat, and blowing dust degraded soft materials such as rubber seals, wiring insulation, fabric, and transparent panels, leaving many secondary systems and exposed surfaces in need of replacement. Once the exterior seals failed, sand, debris, wildlife, and nesting birds entered the fuselage, turning the interior itself into another inspection burden before the team could decide which areas were safe to tow, brace, or rebuild. Because the tires and landing gear had been sitting in the desert for decades, the bomber could not simply be pulled away as found. The team had to prepare the immediate footprint, install serviceable tires and rolling gear, and confirm that the landing gear could carry the loads of a slow overland tow. With no normal flight line support available on the range, even making the aircraft rollable became a recovery operation of its own. The primary wing boxes and fuselage frames were robust enough to survive a slow overland tow. But the next constraint was not inside the bomber at all. It was hidden in the desert floor around it. Federal law protected the desert floor, turning a heavy equipment extraction into a biological mapping problem. The physical recovery of the bomber could not begin with mechanical force. It had to start with a systematic foot patrol. The Bureau of Land Management exercised strict jurisdictional control over the undeveloped sections of the Mojave Desert surrounding the military range. This land served as a designated critical habitat for the desert tortoise. Under federal ecological protection protocols, disturbing or crushing a burrow carried severe operational and legal penalties. The recovery team was prohibited from simply charting a direct compass heading from the aircraft to the nearest highway. They had to navigate a landscape where the primary hazard was biological rather than geographic. This mandate forced a rigid operational constraint onto the towing process. The team planned to use heavy bulldozers to break the bomber free from the sediment and drag it overland. These machines generate massive ground pressure and possess zero forward visibility regarding small terrain features. To prevent accidental habitat destruction, the operation required the implementation of ecological route avoidance. Bureau of Land Management spotters were integrated directly into the heavy equipment team. These specialized biological monitors were tasked with walking ahead of the bulldozer tracks to visually scan the scrub brush and hardpan for any signs of active or dormant burrows. This procedural requirement dictated the speed and shape of the extraction. The heavy equipment could only advance as the cleared route allowed. The bulldozers had the mechanical torque to pull the airframe, but the recovery had to remain slow, deliberate, and circuitous, with biological concerns overriding the desire for a direct line out of the desert. Each change in direction had to be managed carefully because the aircraft's wide span and aging structure left little margin for careless handling. By adhering to the monitored route, the civilian recovery group kept the extraction aligned with the biological constraints placed on the desert floor. The route was checked for tortoise concerns before the heavy equipment and the bomber advanced. The biological mapping problem was managed, allowing the convoy to leave the undeveloped scrubland behind. With those constraints cleared, the team faced the geometry problem of dragging an intact heavy bomber across the landscape. Moving an intact heavy bomber overland required manipulating local infrastructure to fit a massive lateral footprint. Once the ecological boundaries were mapped and cleared, the extraction team initiated the physical tow in 1998. The primary objective was to move the aircraft to a civilian staging area at Inyokern Airport. This required dragging the airframe roughly 40 miles across the Mojave Desert and through local infrastructure that had never been designed around the footprint of a heavy bomber. The team faced a critical handling decision. They could reduce the width of the load only by dismantling the aircraft on or near the range, a step that would add its own rigging, support, and transport problems before the bomber had even reached a workable staging area. Instead, the team elected to tow the airframe intact to Inyokern before breaking it down for the long trip to Kansas. This local decision locked them into an extreme handling geometry. A Boeing B-29 has a wingspan of 141 feet and 3 inches. Dragging it out of the desert was not simply a matter of pulling weight. It was a matter of sweeping a rigid, fragile horizontal structure across terrain that was not perfectly flat. Moving an object with that wingspan means any slight unevenness in the ground acts as a fulcrum. A drop in elevation under one main landing gear wheel lowers the wingtip on that side, threatening to strike the earth, while simultaneously elevating the opposite wingtip. To prevent asymmetric structural loading, the bulldozers had to keep the tow cables perfectly balanced and navigate only the flattest available surfaces. Furthermore, the turning radius of an intact bomber creates a sweeping arc constraint. The inner main gear acts as a pivot, while the outer wingtip travels through a massive horizontal perimeter, requiring wide clearance zones for every directional change. To manage this geometry over 38 miles, the team could not rely solely on natural terrain. The extraction route eventually intersected man-made obstacles and infrastructure. As the slow-moving convoy approached local roadways, the surrounding infrastructure became the primary constraint. Standard 2-lane public roads are roughly 24 feet wide. The Superfortress required nearly 6 times that lateral clearance. As the slow-moving convoy approached developed ground, the surrounding infrastructure became the primary constraint. The extraction convoy took several days to complete the overland journey. The route had to deal with high-tension wires, private property, backyards, railroad tracks, traffic lights, and signage. In places, the obstacle was not weight, but geometry. The bomber's wings and tail turned ordinary roadside features into collision risks that had to be removed, bypassed, or managed before the convoy could continue. Tow crews maintained continuous communication between the bulldozer operators pulling from the front and the personnel walking the extreme edges of the wings. This precise geometry management ensured the degraded aluminum shell did not strike road signs, guardrails, or utility poles. The bulldozers successfully dragged the B-29 across the final stretch of asphalt, parking it safely on the tarmac. The physical extraction phase was complete. The bomber had reached the local airport, but the recovery immediately stalled against a hard logistical limit. Open-air desert facilities could not support the kind of deep restoration dock required, forcing a radical change in recovery strategy. The initial plan upon reaching Inyokern Airport was to execute much of the restoration directly on the outdoor tarmac. The recovery team quickly encountered a severe facility capability limit. An active airport ramp could help stage the airframe, but it did not provide the workforce, tooling, shelter, or industrial support needed to rebuild a World War II bomber to flying condition. The desert environment that had preserved parts of the aircraft during its time as a target now became a barrier to returning it to the sky. Acknowledging this hard operational constraint, the project leadership executed a decisive pivot. They formally abandoned the outdoor restoration plan at the California airport. The operational trade-off was clear. The team had to sacrifice the fully assembled status of the bomber to gain access to an enclosed factory floor. This dictated a complete halt to localized repair efforts. The new objective was to systematically dismantle the aircraft they had just spent years negotiating for and towing intact and ship it across the country. The selected destination was the original Boeing manufacturing plant located in Wichita, Kansas. Returning the airframe to its exact point of origin provided the necessary industrial infrastructure to support a total rebuild. Moving the massive aircraft halfway across the continent introduced a new logistical threshold. The bomber could not be towed intact over the interstate highway system due to hard dimensional limits on highway overpasses and toll booths. To achieve the transport, the recovery crews had to carefully separate the major structural assemblies at their original factory splice joints. They separated the bomber into major transportable sections rather than trying to move the fully assembled aircraft over the highway system. By reducing the single massive lateral footprint into modular loads, the team solved the highway clearance constraint. In May of the year 2000, the dismantled airframe was ready for the road. The operation required a fleet of heavy transport vehicles. The disassembled sections were carefully loaded onto 7 flatbed trailers. This trucking operation required precise load balancing. Each of the 7 flatbed trailers had to be rigged with custom wooden and steel cradles. These temporary fixtures distributed the dead weight of the fragile aluminum shells evenly across the trailer decks, preventing point loading that could crush the lower bulkheads during transit. The convoy navigated the interstate highway network, successfully shifting the recovery effort from a remote desert extraction into an industrial transport operation. This logistical pivot completely bypassed the geometric limits of a fully assembled heavy bomber, trading a 141-foot wingspan for a linear convoy of trucks. The disassembled sections arrived safely in Kansas, but to achieve flight, the team had to replace major components that the desert had claimed. Achieving airworthiness required major structural elements that simply no longer existed on the China Lake airframe. The flatbed transport successfully relocated the modular bomber to the enclosed factory floor in Kansas. Once inside the controlled environment, the team initiated a full structural audit. This inspection verified that while the primary wing spar and central fuselage were viable, several critical assemblies were heavily compromised. The engineering team faced a hard supply chain limit. Aviation supply networks do not stock replacement parts for a 1940s heavy bomber. The team had to manufacture new components from raw aluminum stock using original blueprints, or they had to execute donor airframe scavenging. Scavenging requires locating a surviving static display aircraft and negotiating the removal of a specific component. This is a complex logistical trade-off because static museum displays rarely part with primary structural elements without receiving something of equal exhibition value in return. One of the most visible missing components for this restoration was the vertical fin and rudder. The Navy had sawed that assembly off before the aircraft reached the rebuilding floor, with later accounts differing on whether the cut was made to clear high tension lines or to reduce the effect of desert winds. Whatever the reason, the result was the same. Dock needed a replacement vertical tail assembly before it could become a complete aircraft again. The recovery team mapped the inventory of surviving airframes and located a replacement vertical fin and rudder from the New England Aviation Museum in Windsor Locks, Connecticut. Integrating a donor tail assembly was still a precise restoration challenge. The replacement had to be fitted to Dock's aft fuselage, aligned with the original structure, and tied back into the control system with enough accuracy to satisfy the standards of a flying restoration rather than a static display. With the donor tail secured, the project entered a prolonged rebuilding phase. The restoration stretched across roughly 16 years in Wichita, with major interruptions along the way. The project utilized a workforce of aviation professionals, including active and retired Boeing manufacturing staff. They drilled out and replaced corroded rivets, remanufactured missing parts, and rebuilt systems that could no longer be trusted after decades in the desert. For power, the team sourced and installed restored Wright R-3350 series radial engines configured for reliability in modern warbird operations. Every structural repair, cable tension adjustment, and system replacement had to be documented and inspected. The objective was not merely to assemble a visually complete aircraft for static display. The objective was to satisfy the procedural and structural requirements necessary to legally carry a crew and fly. This required non-destructive testing of the critical wing attach points, pressure testing of the hydraulic systems, and rigorous ground engine run-ups to verify oil temperature and vibration limits. The long restoration culminated in the inspections, paperwork, and ground testing required to return the bomber to legal flight. Federal aviation inspectors and the restoration team had to verify that the aircraft could be operated safely, not merely displayed as a complete shape. In July 2016, the fully restored B-29 executed its first post-restoration flight. The aircraft that had sat exposed on a high desert target range was successfully integrated back into the National Airspace System. The operation transformed an abandoned military target into an actively flying museum, preserving both its structure and its operational legacy.